Sir, this is T. Kushi from ITA, and my roll number is 37. And my topic for concept video for physics is Planck's quantum hypothesis. So let us know about the introduction. In 1900, Max Planck reported his discovery of a formula that accurately described the shape of a blackbody spectrum for all wavelengths and temperatures. Having found an empirical formula that fit the observations, he then sought a physical reason for the success of the formula. Planck's thinking began by supposing the existence of identical vibration oscillators within the walls of a hot cavity. This might be found in any ordinary sized object in which energy radiation is emitted when an oscillator makes a transition from one energy to lower one. Absorption of radiation is an inverse process in which the oscillator jumps from a lower energy level to a higher one. So in transition, generally from higher energy level, it drops to lower one, whereas in absorption, it is the inverse process. Here it jumps from the lower energy level to the higher one. Planck did not draw upon any direct evidence of energy quantization, nor did his results come from existence of classical theories. Instead, he introduced the quantum concept as a modification of classical ideas that brought his theory into agreement with experimental observations. The word quantum has the same origin as quantity and means the smallest possible unit of energy. So when Planck has discovered this Planck's quantum theory, actually it was not based on the classical theories, but instead he developed this theory which was based on the quantum concept, and this was new to everybody. And here in the quantum concept, the word quantum means a small packet of energy, that is smallest possible unit of energy. Planck originally suspected that it was a mathematical trick that did not correspond to reality. However, his formula for blackbody radiation commanded attention because of its striking agreement with observations. The replacement of the view that energy flowed like a smooth, unbroken stream of water by one in which energy needed to be thought of as coming in little packets marked the beginning of quantum physics and the end in which all physical explanations were in terms of continuous flows or motions. So, actually, first he thought it was a mathematical trick, but after that, he has realized that it is not a mathematical trick. And generally, in classical physics, the flow of energy was considered to be a smooth, unbroken stream of flow like water. But when it comes to quantum physics, here energy was taken as small packets. It comes under small packets. So this began the starting stage of quantum physics. So now let us know about Planck's quantum theory of radiation. Planck's quantum theory. According to Planck's quantum theory, different atoms and molecules can emit or absorb energy in discrete quantities only. The smallest amount of energy that can be observed or emitted in the form of electromagnetic radiation is known as quantum. So what is quantum? It is the smallest amount of energy that can be emitted or absorbed in the form of electromagnetic radiations. The energy of the radiation absorbed or emitted is directly proportional to the frequency of the radiation. So energy which is absorbed or emitted, it is directly proportional to the frequency. Planck's quantum theory is a natural phenomena of quantum mechanics. The theory was put forward by German scientist Max Planck. It explains the quantum nature of the energy of electromagnetic waves. Planck's quantum theory deals with phenomena such as photoelectric effect and the nature of radiated emission, which were not explained by the laws of classical physics. The blackbody spectrum, which is the radiation emitted by a body that absorbs all the lights that falls on it, shows significant divergence at higher frequencies. This divergence was at odds with the hypothetical results predicted by the classical model of physics. Planck resolved this conundrum by theorizing that a particle in an oscillation only absorbs radiation with a minimum amount of energy. Radiation with energy less than this minimum amount is not absorbed. The value of this minimum energy was discovered by Planck to be proportional to the frequency of oscillation of the oscillating particle. The relation between the energy required to excite the particle to a higher energy level and the frequency of the particle is given by the following relation. So the relation is E is equal to h nu, where E is energy of the radiation, h is Planck's constant, and V is frequency of radiation. Planck himself determined the value of h from previous experimental measurements of black body radiation, and Planck's constant value, that is h value, is given as 6.626 into 10 power minus 34 joule second. So the unit of Planck's constant is joule second. So here with this picture, you can know the major difference between classical physics and quantum physics. So here you can see a ladder. So this ladder is nothing but the example of quantum physics, and this slide like thing is nothing but the example. That ramp is the example of classical physics. So energy is quantized or restricted to specific levels. This is like how climbing a ladder must be done using rungs. You cannot step between rungs to climb. And come here, so here the energy is quantized. So generally in quantum physics, what are we doing? What are we proving is that energy is quantized. Quantized is nothing but energy is stored in small packets called quanta. So here the best example for this is climbing up a ladder. So when you come to classical physics, here energy is not continuous. That is, climbing this ramp, you can stop at any point. A ramp does not have discrete or specific values like energy. So this is the difference between energy which is quantized and energy which is continuous. The major difference between classical physics and quantum physics. And here is another example. It is nothing but, the way you climb. So climbing upstairs is an example of quantized energy. That is the example of quantum physics, whereas climbing a ramp is an example of classical physics. Potential energy of a person walking up ramp increases in uniform continuous manner, whereas potential energy of a person walking up steps increases in stepwise, that is in quantized manner. So this is one of the example for knowing about quantum physics and what is quantum energy and why is it quantized. So generally in quantum energy, the energy will be quantized in a step-by-step manner. So Max Planck explained it by assuming that energy comes in packets called as quanta. Quanta is nothing but packet of energy. Planck's quantum theory states the following postulates. So there are a few important postulates of Planck's quantum theory. Let us look into it. The energy is not radiated or emitted continuously. It is emitted in small portions in the form of energy packets called as quanta. Radiation, when in the form of light, each particle is known as photon. Photons are energy particles of small proportion in the case of light. The next one is the energy of a photon or quantum of energy is directly proportional to the frequency of the radiation. That is, E is equal to h nu, where h is Planck's constant and V is the frequency of radiation. And the fourth postulate is that the total energy of radiation is represented as a whole number. So it is generally represented as a whole number, and multiple of energy of quantum is given as hv, 2hv, 3hv, and so on. Generally energy is represented by a whole number. So once let us know in a brief way what are these postulates. The first one is that energy is not radiated or not emitted. So here in quantum physics, energy is not being radiated or not being emitted. It is emitted in small portions in the form of energy packets called quanta. Coming to the next point, radiation when in the form of light, each particle is known as photon. So when radiation takes place in the form of light, here the each particle is known as a photon. So photon is nothing but light, energy of light. And coming to the third point, energy is directly proportional to frequency into Planck's constant. That is, E is equal to h nu. And the total energy of the radiation is always expressed in the form of whole numbers. For example, it may be hv, 2hv, 3hv, so on. The discovery proved significant in the later development of quantum mechanics. Planck's results showed that electromagnetic waves behave both as particles and waves when interacting with matter. So from Planck's results, we got to know that electromagnetic waves have dual nature. That is, it can act as particles and it also has the wave nature when it is interacting with the matter. This dual nature of electromagnetic radiation led to further investigations by de Broglie. He was successful in obtaining a formula for the wavelength of any particle with mass and momentum. The relation between the wavelength of a body with its momentum is given by lambda is equal to h by mv. So from Planck's quantum theory, we got to know that electromagnetic wave has dual nature, that is particle nature and wave nature. So with the help of this theory, there was a relation which was being developed by de Broglie. The relation between wavelength of a body with its momentum was discovered, that is lambda is equal to h by mv, where h is Planck's constant, lambda is the wavelength, m is the mass of the body, and v is the velocity of the body. So generally, if coming in the case of velocity of light, you take v value as 3 into 10 power 8 meters per second or 3 into 10 power 10 centimeters per second. These are standard values when you are taking it as velocity of light. So here you can see the black body radiation curves, which is drawn between intensity and wavelength. So you'll have ultraviolet rays, ultraviolet region, visible region, and infrared region. According to the colors, you can differentiate these regions. So here is an example. Wavelength of a quantum of radiation is given. What is the wavelength of quantum of radiation whose energy is 3.05 into 10 joules second? So here energy is given. You have to find its wavelength. So what is the formula? E is equal to h nu or hf. Nu is nothing but frequency. Instead of nu, you can also write it as f. So E is equal to hf, and formula of frequency is c by lambda. So E is equal to hf, that is equal to hc by lambda. The wavelength is obtained in the following way. Lambda is equal to h into c by E. What is the value of h? Planck's constant value is 6.626 into 10 power minus 34 joules per second into 3.00 into 10 power minus 8 meters per second. I already told you, when you are taking velocity of light, it will be c, and the value is 3 into 10 power 8 meters per second by energy. What is the energy value given? 3.05 into 10. So after all these calculations, you'll get the value of lambda as 652 nanometers. So what are the advantages of Planck's theory? It explains the energy spectrum of the black body radiation. It is used to deduce Wien's displacement law and Rayleigh-Jean's law. And it introduced a new concept, that is energy is absorbed or emitted in discrete manner, that is in terms of a quanta of magnitude of hv, that is E is equal to hp or E is equal to n into hp. So comparison between Planck's quantum theory and classical theory of energy. So coming to Planck's quantum theory, in Planck's quantum theory, energy of electromagnetic radiation is quantized, that is, it is discrete. Whereas in classical theory, energy of electromagnetic radiation is continuous. And in Planck's quantum theory, energy of electromagnetic radiation depends on its frequency or wavelength, that is equal to E is equal to hf. Whereas in classical theory, energy of electromagnetic radiation does not depend on its frequency or wavelength, but it depends on its intensity. So these are the major differences. So let us know the applications of Planck's quantum theory. Planck's quantum theory is the fundamental theory of quantum mechanics. So it has applications in all those fields where quantum mechanics is being used. So it has applications in electrical appliances, the medical field, quantum computing, lasers, quantum cryptography, etc. So these are some of the applications where Planck's quantum theory is being used. So coming to the conclusion, the significance of Planck's constant in this context is that radiation such as light is emitted, transmitted, and absorbed in discrete energy packets or quanta determined by the frequency of radiation and the value of Planck's constant. He proposed that only certain amounts of energy could be emitted, that is quanta. Classical physics held that all values of energy were possible. This was the birth of quantum theory. Planck found that his new theory, based on quanta of energy, accurately predicted the wavelengths of light radiated by a black body. Thank you. I hope you understood this session. Thank you so much.